Hello, let me present the screen, entire screen. So, screen one, I have to so, yes. Okay, so I hope I am audible to everyone. And yes, so in this particular lecture, we will be going to solve some of the question which has been taught in third week of the course, multiphase microfluidics. And this multiphase microfluidics actually initially you started with different kind of flow regimes, uh, and then you gradually shifted here. In this week you started with the computational fluid dynamics and what are the different computational methods which are being used in solving and predicting the flow behavior. And then in the subsequent lecture you have been taught about this wetting and jetting and dripping regimes, and then at the end you have been there have been discussion about the surface tension and surface energy. So I will be solving some of the questions which are directly or indirectly related to the various concept which has been taught within the week, that will be helpful for you in solving the assignments that are that is provided to you. So I will begin with the first question. So I will be solving these questions meanwhile, but at the same time I will be writing some of the question and solving at the same time. So like for example, how how different flow regimes are controlled. So examples are volumetric flow rates of continuous and disperse phase. So let me see if somebody came. Yes, admit. So for you have been taught about this computational fluid dynamics, and then different flow regimes, especially jetting and the dripping. And then in the last lecture of the week, there has been discussion about surface tension and surface energy and their Young's equation and the fluid between two plates, and also rise and fall of the capillary. So those questions I will be addressing. So this particular question that I will start with is how different flow regimes are controlled. Option A is volumetric flow rate of continuous and the dispersed phase. Another option is viscosity stratification, then gravity, then density stratification. So what are the different uh, in order to control different flow regime, for example, jetting, dripping, and there has been some discussion about the Rayleigh-Bénard instability. So this Rayleigh-Bénard instability that involved this, for example, from the tap, this is the tap. Let me draw tap clearly. Yes. So from the tap, this is the hook of the tap, and water is falling. So you see that this forms the jet first, and this jet which is here, this jet first go straight, and then dripping starts. So small droplets forms, and this happens because this interface of the fluid, for example water, this interface gets undulated because of the Laplace pressure gradient at the interface of the wall and the water and the air, and that gradually leads to the breakage of the jet. So at what particular wavelength this breakage will be happening? If you actually dig deeper into this subject, you will come to know that if length is 2 root 2 times of the diameter of the jet, then there will be breaking, condition for breaking. Though this involves various assumptions like uh, uh, lubrication approximation, but yes, this is the rough estimate that has been calculated analytically using Navier-Stokes equation and the continuity equation, that at what particular condition there will be breakage of a jet, and this comes under the umbrella of Rayleigh-Bénard instability. Rayleigh-Bénard instability. So if you actually see in this particular problem, different flow regimes are controlled by what? So like different flow regime, if I talk about, like I will be discussing with some of the good videos which are there, accessible to everybody. So I will be giving them reference, and these different experimental and the theoretical videos are there that actually dictates that how different physics is playing its role uh, in getting different flow structure and the morphology. And if I actually go into this, then uh, the first one is uh, like you see, if this is visible to you, the first one is the dripping. So from here you see there is the nozzle, and from this nozzle one dispersed phase is coming and surrounding is the continuous phase. Both the phases are having their own volumetric flow rate and the velocity, and you see dripping regime means once the drop comes up, once the fluid dispersed phase comes up, gradually it makes and splits into the droplets. And another one was this this you see, another one was this intermediate dripping. So here you see there is somewhat stretching and thinning of the thinning, and the droplet size is somewhat more. And you see this particular thing is happening when you had dispersed phase velocity to be more. And the last one is the jetting regime. So in the jetting regime, there will be discontinuity and different size droplet you will be having. Some will be more in their diameter, some will be less. But this is the main thing. This happens between the interplay of this Weber number and the capillary number. So this particular regimes, which regime will happen when this will be dictated by viscous force, inertia force, and the surface tension force. And this, you see, the second lecture of the week was completely dedicated to these three regimes and why this happens. So we will be looking at those things with some of the example, and subsequently we will be revisiting these lectures and these videos in order to get things cleared. So this particular question that I am talking about is how different flow regimes are controlled. And option A is volumetric flow rate of continuous and dispersed phase. So different flow regimes are controlled definitely by the volumetric flow rate of continuous and the dispersed medium, and then viscosity gradient. So yes, when you was in the this different regimes, there will be different flow structures coming up, and which regime will be affected more by viscosity stratification, density stratification, or the volumetric flow rate. That will be another aspect that is controlling the flow structure and flow behavior. So droplet breakup in T junction. So what actually happens there is like all these forces are responsible, but some of the forces are responsible for some kind of morphology and another is for another. For example, for squeezing regime, pressure drop induces breakup. So pressure drop is the main thing, and this squeezing regime at the low velocity, it happens at the low velocity and small capillary number, which is capillary and the Weber number is small, like 0.01. If capillary number is 0.01 or less, your Weber this squeezing regime will happen. So as squeezing regime, when this will happen, and what is this squeezing regime I will be talking about, when this pressure drop is inducing the pressure drop is inducing the breakup. Okay, and another one is like it happens at it happens at low velocity, low velocity. And the third is the capillary and the Weber number. The and capillary and Weber number, these should be small. So is there anybody, can you tell about capillary and the Weber number? Like what are they? Can you define the capillary and the Weber number? Somebody was there. I just Sizu RS. Can you please prompt up? Then these things will be like discussion and it will help us. So if things go one way, then there will be like no questions arising. To make the overall lecture interesting, if you cooperate, it will be good. So this capillary number is the one and the Weber number is the another, and both are them having surface tension to be one factor. So this capillary number is what? This is viscous force to the surface tension force. So this viscous force to the surface tension force, this viscous force to the surface tension force is the one that will be actually narrating the taking care of different morphology and squeezing and bending and breaking of the droplet at play. So this this capillary number, if you define it, then this capillary number is what? This capillary number is viscous shear force, viscous shear force to surface tension force. Surface tension force means this is what? This is this is what? If you see, surface tension force is what? Sigma is the surface tension divided by L, and this is what? Viscosity times U by L. So this will come out to be mu U divided by sigma is the capillary force. And what is Weber force? Capillary number. And what is Weber number? Weber number is inertia force to the surface tension force. Inertia force to surface tension force. And when you look at this comes out to be rho u squared d diameter divided by surface tension, which is sigma. So these two numbers are deciding, and these two numbers are defined in terms of forces, and these are deciding factor for the different regime. For example, the squeezing regime. So squeezing regime will be dependent, and then this particular thing like dripping regime. If you see dripping regime. So this dripping regime here, shear stress on the droplet play a significant role. Okay, so this you see, shear stress means what? Viscosity thing will be coming into picture, because that is the one that will be taken care of. So obviously this viscosity will be one other factor for controlling the flow design, and then the gravity. So G is acting here. So definitely G is having some role in deciding this length scale. So G is also another reason. And this density stratification is what? Sometimes density is responsible for Rayleigh-Taylor instability. So there will be another kind of instability which is coming into play. For example, Rayleigh-Bernard instability was the one. Rayleigh-Bernard, no, Rayleigh-Plateau instability was the one that that is nothing but falling of the tap water. Rayleigh-Plateau instability, this one. And Rayleigh-Bernard is what? Rayleigh-Taylor is what? If the density of two fluids are there, density 2 is greater than density 1. So this is more denser, then what will happen? There will be inversion. This more denser fluid will come down and the less denser will fluid go up. And meanwhile, when this inversion is happening, that process is termed as Rayleigh-Taylor instability. So that will also be there in deciding the morphology of the thing. So all of the options are correct in the question. So if you see, this squeezing regime is because of the pressure drop, and this dripping regime is because of the shear stress on the droplet. So here what happens? Shear stress on the droplet plays important plays significant role or important role. Okay, that's the one thing. And this happens when it happens in T junction or T junction. I will be showing some videos from there. You will be clearing it up. T junction or a co-flowing device, and this happens at higher flow velocity. Here, what we had, this happened at it happens at low velocities. It happens at high velocities. This one happens at high velocities. So fluid velocities will be high, then this will happen. And this is a squeezing about a squeezing regime and the dripping regime. And what about dripping jetting regime? So this jetting regime is also one thing where there will be a jet stretching up, and then the subsequently that jet will get broken up. Like this usually happens at the higher capillary number. Like this in the lecture also sir has explained. I will be showing you, so this will be clear to you. See here, different regimes when sir was explaining, you see. So yes, no, here, yes, this is the T junction. There can be Y junction, and there can be continuous disperse and the continuous phase coming up in the conflow flow devices. So this is conflow device, and if you see this conflow device, T junction and the Y junction, everywhere, what are the things which will be playing their role in deciding which morphology will be coming up, whether it will be jetting, dripping, or squeezing, or transient of both. So that is decided by flow rate of the continuous medium, flow rate of the dispersed medium, density of the dispersed, viscosity of the dispersed, viscosity of the continuous, density of the dispersed, density of the continuous, and then the diameter of the channel, and then the geometrical diameter and differences in the ratios of the diameter from where both the fluids are coming in. So this these entire factors are responsible in deciding the flow behavior inside the microfluidic channel. And then this squeezing, dripping, and jetting, these are the regimes, and these happens at different capillary number and at the low and the high velocity. And jetting regime, when you see this jetting regime, that comes up when the capillary number is pretty high. So see, squeezing regime is happening at the capillary number of 0.004. Okay, and this dripping regime is happening at the around capillary number of 0.035. So 0.004, a bit higher capillary number gave the this dripping regime. And when you go further higher, this was 0.035 and this is 0.05. Then this comes up at this jetting regime. So some question could be asked with from you, like like if I tell you, like we have solved this was a six question. Seventh question is like what could be the respective order, respective increasing order of capillary number for getting squeezing, dripping, and jetting regimes respectively. So options are this is 0.05, 0.035, 0.004, then 0.004, 0.035, 0.05, then 0.05, 0.004, then 0.035. None are there. So what is the correct answer? So if you have listened to the discussion that we had, is this one, like these are phenomena, these are there, these are happening. So let me take them at same level, so things will be a bit clear to you. And these are things, these all are happening at different flow regimes, and thus they are actually responsible for different features which are coming up. So this is the first one, which is squeezing regime, and it is happening at the capillary number very low, means the velocity is very low, and velocity is actually dictating uh, its flow regime, like which structure is coming up. So there you came to know that that is the squeezing regime. And then when you see another one where you have increased a bit the velocity, so the capillary number, and you had another regime which is called dripping regime. So here this dripping regime is having more capillary number than the squeezing regime. And another one is like the one which we were talking about, and I will be showing you some experimental evidence of the same, is the jetting regime. And this jetting regime, if you see, is the one that is at very high capillary number. So which of the following is correct? Is like squeezing, dripping, and the jetting. So jetting happened at very, class is going on. Okay, yes. So this jetting happens at very different, a very high capillary number. So if you see, one minute. Actually, class is going on. Yeah, sorry, somebody came. Yes. So this decides this 0.05 for the dripping. Very low. Very low is what? Very low is this one. This is for the squeezing, and then for the dripping is 0.035, and for this one. So option B is the correct answer for the same. So that is the one thing that I wanted to tell you. And then if you actually look at some other questions that I had already. This question I have already solved, how different flow regime. So we came to know that different values were responsible. So though I have taken these only, density, viscosity, gravity, and this, but these are the different reasons that will decide which flow structures will be coming up into the picture. And very clearly sir has explained in the lecture also, and there you get to know more about the same, like q continuous, q disperse, mu d, mu c. So this is viscosity stratification, density stratification. Dimension is obviously the one reason, and the flow rates. So that is the one thing. So if I tell you the question now we will be solving is, which of the following is correct for momentum balance equation in the fluid dynamics? So first of all, the momentum balance equation in the fluid dynamics is what? The momentum balance equation is the Navier-Stokes equation. And there is different options which have been given to you to decide which of the following is correct regarding the Navier-Stokes equation. So just approach this problem and let's see how well you go. So this particular question is which of the following is correct for the momentum balance equation, and this this the option A says it's partial differential equation. Another option says it's ordinary differential equation. C option says it has multiple dependent and the independent variables in it. And the last option is can't be solved analytically if you want to solve it fully. So just attempt this problem. Meanwhile, I will be I will wait so that I get something out. So it's like that. One way is like you are going to solve the assignments which are being posted at the SWAYAM website, and another is like before attempting the assignments, if you go through these lectures which are there that are specifically designed in order to have somewhat discussion about the content through the quiz or questions related to the content which is provided in the week. So they're similar or somewhat related questions you will be getting your assignments. So that will be the one thing that will help you to get through the assignments. And also you can raise your doubts at the here also, and at the same time you can raise your doubts at the ask section of the website, like you can ask question there in the community. So just look at the problem. So if I write the Navier-Stokes equation, then the things will be very easy for you, but it will be good you if good for you if you just attempt once, like what are different reasons for this. So definitely when you have looked at the Navier-Stokes equation, you have seen that at the numerator you are having this velocity in x direction, that is u, velocity in y direction, that is v, velocity in z direction, that is w, and then you are having pressure also in that. There is a force of gravity also. So there are different variables, and these variables are the dependent variables. And if you see, and if you talk about the independent variables which are there and which are playing its role, are the time and the xyz. So time and the space coordinate, that is xyz, they are anyway forming up some important reasons. And this particular equations will be they will be deciding the flow behavior and the flow feature. So I will be showing you one computationally computed uh, uh, phenomena through the numerical simulation, through the computational fluid dynamics for the experimental setup. So from there you will be getting somewhat understanding and insight what sir was talking about when he was telling that CFD, computational fluid dynamics, something about the volumetric volume of fluid method, and then single fluid method, and then discretization kind of thing. So that will be a bit clear to you. So another is like if I tell you this, yes, here if you see, the one is Navier-Stokes equation is what? Del rho v by del t. This is the transient term which is depending on the time marching, and this is the v cross v. and minus delta P, which is grad of P, a derivative of P, plus mu del V plus del Vt plus, if you consider body force to be gravity, rho g. So if you write it in the reduced Cartesian form, you will be getting del u by del t, take rho to be common, plus u del u by del x plus v del u by del y plus w del u by del z, okay, equals to minus del p by del x if you are writing momentum equation in x direction, plus mu del 2u by del x square plus del 2u by del y square plus del 2u by del z square, okay, plus rho gx, gravity in x direction. So here you see you are having different dependent variables. So here you are having u to be dependent variable, okay, p is the dependent variable, and x, y, z, and t are the independent variable. And at the same time, when you will write for the y direction, then you will getting here v, and for the z direction, you will be getting here w. So these u, v, w, and p are dependent variables, and t, x, y, z is the independent variable. Okay, and you see that if there is more than one independent variable, it's called partial differential equation. So this is a partial differential equation, and this is partial differential equation, and it has multiple dependent and the independent variable. And yes, to solve it fully, you need numerical and the computational method. Analytically, it cannot be solved fully. So option A, C, D are the correct answer. A, C, D is correct. So this question is completed. Now going to the another problem is, what are the systematic steps for diving into the CFD analysis? So suppose you have done some experiment and you want to analyze that through the fluid dynamical equation, and for that you are being told that you use CFD analysis. So what is the step through which you will be jumping into the problem and going to get something at the end, or analyze the forces? For example, if I tell you, and if you see this here, okay, this is there. So if you see this, uh, suppose this phenomena that we were talking about is this one. Like if you see, you will see this, like there is three regimes happening: dripping, intermediate dripping, and jetting. So if you see it thoroughly, and this is high speed. First of all, this has been taken in high speed, and this, if you see through the reference, you can go to the actual literature for the same, but you see this dripping, intermediate dripping, and jetting, how this is happening. Here you see this jet is coming up, and through that, so if this has been done to track in the computational theme, so see how this has been done. So this is T junction, though that was in the co-flow device, but if it happens in the T junction, the numerical simulation predicted the same. You see, this is the jetting. First, initially you had dripping, Everything is controlled by the flow rate. This is the dripping which is happening. You see, this thinning is happening, neck is forming, and then breaking of the neck is happening. But when you see, this is jet forms, and then that trickles and breaks. So, so if you actually look at this, you will actually realize that the physics that are at the play in the experiments, you can CFD will tell you more detailed analysis of the same. For example, through the experiments, you will be having high speed facility, then you will get the flow regimes, what size it got broken, when it got broken, and somewhat analysis of the flow rates. But if you actually analyze it through the CFD, you will get more detailed, and the force calculation also at different locations of the drop, different location of the continuous and the dispersed phase, and those kind of intricate depth analysis could be done through proper CFD modeling. So what are the systematic steps for diving into a CFD analysis? So you just look at this and go for this. Meanwhile, I will be telling you what it is and how you can go for the same. For your kind information, this has been explained in the first lecture of the week, which was about computational fluid dynamics. Second lecture was about dripping and the jetting regimes, different regimes in the microfluidic setup. And the third was the surface tension and the surface energy. So, if you see this, why CFD comes up. So actually, this was one was the momentum equation and another was the mass balance. So definitely they are the one that will be solved. But how you will look at the problem. So first is like answer is first what you have to do. First, what you have to do. Let me see if somebody texted something. Is there any text? No. Yes, I am online. Yes, so yeah, like you have to decide your domain. So you have to decide the computational domain and its boundary condition. So you have to decide computational domain and its boundary condition. Okay, that is the first one. Second is once the computational domain and the boundary condition is decided, let me take this to at the bottom so that discussion becomes a bit easy. Yes, yes. So once you decide it, you have to yeah, in those boundary condition you have to give velocity boundary condition, pressure boundary condition, stress boundary condition, and if there is free stream, then free stream boundary condition. So those about what Dirichlet boundary condition, Newman boundary condition, combination of both Dirichlet and Newman boundary condition. So that thing is the a bit involved. So when you go deeper into the subject of CFD, you will come to know about that. But the basic structure to dive into this CFD domain is first you decide the computational domain that you want to solve and then decide its boundary condition. Second is discretization, convert partial differential equation into algebraic equation. So that is discretization. What is discretization? It is converting partial differential equations to algebraic equation. Algebraic equation. And this is done. You can do it. This discretization could be done in space or in time, and in that this is done through meshing, like mesh generation. So, and another is in time you can do it explicit and implicit methods. There are different methods. So explicit and implicit methods. Okay, so that's the one thing. So different discretization methods are there, like finite volume method, finite element method, finite difference method, finite element method, finite difference method. So I will be telling you a bit about this finite element, finite volume, and finite difference method. So for example, if you go for finite difference method, then finite element method, and then finite volume method. So commercially, you may have listened about different softwares that are being used. So MATLAB can be used for all, but mostly MATLAB is being used for MATLAB and Python can be used for coding through finite difference method, or Fortran can also be used. As GUI for the MATLAB is easy, you can go with that. Then finite element method based software is the COMSOL multiphysics. So this is used to get information, especially when fluid is interacting with the structure. So very good method. And then finite volume method based GUI based software is GUI based software is finite volume method based GUI based software is ANSYS Fluent. There are some other finite volume based methods like Jeris, Basilisk, Basilisk. These are there. But yes, these are some rough estimate, rough figure, rough names of the software that are being used, and the behind their methodology and internal discretization is done through these different discretization schemes. So that's the one thing. First is you have to decide the computational domain, and another one is uh, you have to have discretization. And in discretization, you can do it space and time using FVM, FDM, and FEM. Okay. Then the next is once you have done the discretization and all, and discretization has been explained by Sir through through uh, one space problem. For example, this one you see it has been properly explained how FVM is applied for assuming phi to be linear function. It has been applied here at the pole, and this finally you get from the differential equation to the algebraic equation using the discretization methodology, which is FVM, that could be used. And when you actually see this, that is done. And next two step is last but not the least is the solving the equation. So different methods could be used. Once you had algebraic equation, you have to solve the equation. So solving solve the equation. So that can be solved by different methods. Some of the methods are Gauss Seidel, Gauss elimination, LU decomposition, and sometimes people use another method which is called point Gauss theta, line Gauss theta. So you can write it point or line. Okay, etc. So, so once it is done, the last is the post processing. Post processing means analysis of the result. Means extracting the quantities of interest. Extracting variables of variables of interest. That is that. So that was all about the second question that we were solving. The next question is what discretization does. What discretization does. As we talked just once about this, what is done by discretization? It actually changes the partial differential equation to the ordinary differential equation. So the second question explanation explains third question also. So it reduces ordinary into partial differential equation, partially into ordinary what? It reduces partial differential equation into algebraic equation. So this is correct and all are wrong. So it is done. The fourth problem that is there is what? Is this one, which is which of the which assumption is used for solving. So I was talking about this, like where sir told about this conversion of I mean from partial differential equation to organic differential equation, how discretization is being done. So they have assumed what? Watch profile. So they have been, you can assume different profile, but in the explanation it has been assumed to be linear profile. So linear profile has been assumed for deriving that. And next problem is the one we will be talking about is this one. You see this one, what it is like, which of the following is different approach for solving fluid flow problem. So you can solve it experimentally, you can solve it analytically, theoretically, or numerically, and computational fluid dynamics is another aspect. So which of the following are different approaches? So as we have had discussion and I have shown you two videos also. So you see these videos. Uh, so no, nothing is there. Yes. So it, like ninth video, if you see this is the annular region is coming up. So annular region is coming up. If you see later when the flow is changed, this happened. So these fluctuation came up. So one is the water and the another is the oil. Oil is pushing it, water is coming here, and you see at the same time Rayleigh plateau instability is also leading to some droplet formation. And this particular experimental thing, if you want to do it computationally, then you have to decide your model system as per the experimental geometry. See, this is the sludge formation. When the volumetric flow rate of the two fluids are in such a way that the water flow rate to the oil flow rate is a bit high, then there will be more water volume of the water being collected, and you see, and here you see there are, this is a kind of Taylor flow kind of thing happening. But the Taylor flow, about the Taylor flow that has been explained, that was air gas was there at that position, where in this case you are having water. So oil is this one, drops are of water, and in the case of Taylor also similar phenomena we have observed. So this is the one. And if you see another one, if I can tell you, yes, if yes, this one. So this stretching happened. See, you see that, you see this, how these waves are forming. There is a competition between different flow structures. Yes. So let us get back to the question and the problem we were talking about. And this different. So first is like, you know that for two-phase flow, if you are solving, you have to solve continuity equation and the Navier-Stokes equation for the different flow phases. And if you solve them, then there will be different condition. So the question is if I tell you this is why sixth we have solved, I think sixth we have solved, this was seventh. So let us solve question number eight. Question number eight, let us solve is, what are different boundary condition? What are different boundary conditions that need to be considered, need to be considered while solving two-phase flow, two-phase flow problem. So what are they? Here there is no option. You have to just point them out, and then we will see what are they. So like different boundary condition you have been taught about, explained about, and in the lecture also when sir has told you about deciding your computational domain and the boundary condition, there he has told pressure condition, velocity conditions, shear stress condition, that has to be considered. But especially if you are going for the two phase flow problem, then there is something called this. If suppose this is the interface, so in this direction there will be one, for the first phase there will be a tangential velocity component coming up. For the other velocity component is, for the first phase there is the normal velocity component. Similarly for the second phase there will be normal velocity component and there will be some tangential velocity component. Okay, so this particular thing explains that there are some kinematic conditions. So kinematic condition that has to be considered. Okay, so kinematic conditions are like continuity of velocity. Okay, obviously this will be there for the tangential direction also and for the normal direction also. That has to be there. If there is no jump, then if I actually tell you why these are important things, then 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 you actually come to know about that. So for example, if we see this, okay, let me see. Let it take this side. Yes, if you see this, uh, different boundary condition when we talk about, then these are some of the boundary conditions. So this slide of the lecture explains about the same. These are different boundary conditions that has to be taken in account. And then the one boundary condition that we have already looked at while getting to know that what are the different steps of going into diving into the CFD problem. And there you came to know about the defining the domain and the boundary condition. So when you define the domain and the boundary condition, you came to know about no sleep boundary conditions, pressure boundary condition, and different other boundary conditions. So if you see them, so those are also one thing that has to be considered at the inlet, at the outlet. You need to consider different boundary conditions. So that is the one thing. And in the interface, there will be four main boundary conditions. Continuity of velocity in the x direction, continuity of velocity in the z direction, y direction, or the tangential direction. And then there will there will be something there will be something called what this continuity of velocity in the that is there. Then tangential balance equation and the normal balance equation that will be coming up into the picture. And that that if you consider tangential balance, normal balance, and that thing, then that this, if I tell you, there it will be continuity of velocity at the interface. Okay, in x direction, in y direction, both direction it has to. Suppose it is 2D problem, then normal balance equation, and then another one is tangential balance equation. So this tangential balance equation, normal balance equation, and different equations, they actually played their role in deciding up whether the system is getting some kind of instability at at their interface and leading to some flow structure, or they are just trying to get their stable situation and be in the stable uh, structure. So this particular explanation actually tells, for example, if I just from the slide only, class slide only, I will be taking into the main slide. See, this is the another boundary condition. This is the normal balance boundary condition that has to be considered, and the tangential balance boundary condition that has to be considered. And if there is a Marangoni flow or the surface tension is changing with the temperature, then further some of the Marangoni number and the Marangoni factors coming up into the equation. But the main concept is this one only. So the next problem that we will be solving is interface tracking. So like what are the different methods that you use for interface tracking and what is interface tracking. So, so the another question is what is interface tracking? Ninth, what is interface tracking? So what is interface tracking? Or or interface capturing, if you say interface or interface capturing. So interface tracking or interface capturing is the one that is here. Like if you see them, this actually explains it. This is the interface tracking thing. So the fluid is going and one drop is forming in the continuous medium. You see there is the distinct interface of drop and the continuous medium. But if you want to get that theoretically, then you have to have some function that will actually tell the numerical code that this is this medium and that is that medium. Like there should be a exact interface coming up. For example, in this computation, you see they have exactly defined the interface. So once they have exactly defined the interface, the analysis become a bit easy. Okay, the analysis with the exact interface you are getting, and this actually comes up when you are getting fine grid. So grid also matters. Number of grids also matters. Number of mesh also matters in deciding whether your result and how much close the result is. But the convergence should be reached. So so if you go for this, the interface capture that you were talking about, this the interface capture is the interface between the phase is captured explicitly. So that is captured explicitly, explicitly, and this is done by solving an additional equation. Additional equation. Additional equation is solved to track to, to mark, capture, track for the interface between two phases. Okay, so that is the one thing. And if you see this, what happened? Let me see. What happened? Yes, yes, I am there. Yes, so this is the one thing that you need to solve an equation in order to capture the interface. So for example, suppose this is the condition in the fluid scenario, and this is the medium. So you have to solve a differential equation in C. Differential equation in C. We have a dependent variable C. So suppose C equals to 0 is first phase and C equals to 1 is second phase. So this is the first phase, suppose this is the second phase. So accordingly you have to decide the thing. So various phases are treated as one fluid with a variable material property that change abruptly at the boundary. So at the boundary condition, the change has to be captured properly in order to have the exact interface. So transport rate at the boundary are accounted for by adding singular terms in the equation. So that is the one case. And this, if you see, then what equation? So this is the different equation that I was talking about. This is the C0 situation, this is a C1 situation, and you are actually solving another phase equation that will actually take care of phase. So substantial derivative of C is 0. So challenge is different fluid need to be identified in some way. So a marker indicator function is used. The marker function takes different value in the different fluid. The marker function must be updated to account for the moving interface. So this is the marker function, and that has to be updated to account for the moving interface. And a critical and the difficult step is this one only if the interface is moving. So there are different methods like level set method, phase field, moving mesh. So those are being used in order to track these interface. So like if I tell you level set, phase field, moving mesh. Sometimes people use Ken Hillard method. That is also there. So the to track interface. So here the surface tension is also incorporated. So that is the one thing. And now if you look at different thing, so this is also called color function. This one, also called color function that actually decides the phase. And then so what is the two equations very important at the interface? So question number 10 is two very important parameters to define interface. What is the two very important parameters that will define the interface? When you think about that, this was there. So about the dripping and the jetting design, we have already discussed. We are actually discussing the CFD one. And meanwhile, last half an hour, we will be solving 3 or 4 questions based on the surface tension. So that will be numerical problem. Though in the previous lectures also we have talked about surface tension, numericals, questions on surface tension. But in this one, I will be discussing a bit more about that. So around 4 to 5 problems we will be solving about surface tension, the last lecture. And then we will be looking at then we will be concluding the lecture. So two very important parameters to define interface is so so is the what. So if you see, I will be going for that. It is the normal to the interface. So if the interface is there, medium 1 and medium 2 is there, so there will be something tangential and there will be something normal. So if you go for that, then the very most important thing about this interface is its curvature and its normal. That will define it. So normal to the interface is defined as normal to the interface. Interface is defined as Gap equals to grad of color or grad of sieve. So actually taking care of it. Then here is a curvature which are on the interface. That is k equals to L dot m. Okay, so that is another one. And surface tension is what? The pressure normal stress jump at the interface. The pressure normal stress jump adding a body force to the Navier-Stokes equation. Sometimes the Navier-Stokes equation rho g will be if the gravity is there, so that will be considered. Otherwise, at the place of rho g, there will be FST, like surface tension force will be coming up. And so surface force models are there, different continuum surface force models are there, and those are being used, uh, uh, and force is being added into the Navier-Stokes as if it is a body force. So that is the one thing. So what is volume of fluid uh, method? So what is the volume of fluid method? If I want to discuss with you volume of fluid method. So we have solved how many questions? 10. This is the 11th one. Volume of fluid method. Okay. Okay. So volume of fluid method. Option. What is correct? What is correct? Which one is correct for volume of fluid method? Okay. Option A is volume of fluid method. Mass is not conserved. Okay. Option B is mass is inherently conserved. Conserved. Okay. Okay, that is there. Mass is inherently conserved. Okay. A B C option is density and viscosity is assumed to be dependent on phase field parameter like alpha or C. So is this true? And the D option is interface will be diffused over few cells. Okay. So which of the following is correct about the volume of fluid method? So you just try to solve it. These all the questions that I am posting up here is the multiple choice questions. Like you will be having multiple options correct, but in the test you will be getting single option correct. So though there only one choice is given, for your practice we are having here multiple choice question. so that more engaging thoughts can be built and more discussions can be done. So you read it, you solve it, and we will be discussing a bit about this. So you can also reach to different lectures that are being there, that are being provided, and these all the recordings, these practice sessions also are being recorded, and that will be posted on the same systematic course website. And this, if you think about this, what the volume of fluid method was. So if you solve this and if you remember the discussion in the class, you are being told that there is the conservation of the mass and density and the viscosity, they have been taken to be, this has been taken to be function of uh, alpha, which is the parameter that is actually learning its role. So suppose C is the alpha that was taking care of the phase based on the value of C to be 1 or 0. So for example, del alpha by del T plus V dot del alpha equals to 0. And here if you see this, this is alpha 1 plus alpha 2 equals to 0. And from here you get density to be rho 1 alpha 1 for the phase 1 and its fraction, rho 2 1 minus alpha 1 is the fraction. Similarly for the mu 2, mu 2 1 minus alpha. Okay, these are approximate. So that is the one thing. And the interface will be defined over few cells. So if you are near diffuse, this is diffused over few cells. So this is correct one. This is also correct one. So BCD is the correct answer for the given problem. And the last problem of the lecture one that I want to pose to you is this one. Question number, I think we have already did 12, no, 11. Question number 12 is, what are further issues? What are further issues in two phase flow modeling? So in this particular slide, sir has discussed about like you have solved about the fluid flow and two phase flow, whether two miscible or immiscible fluids are there or the two phases are there. So based on this, there will be one problem is like contact line singularity. Contact line singularity. Singularity. Another one is the dynamic contact line. If the contact line is moving, this motion is there. There you cannot consider that there is no sleep condition. So there is some that there's sleep condition. So this is the problem, like dynamic contact line, contact angle. Another one is capturing thin film breakup and collisions. Capturing thin film breakup and collisions. Another one is a phase modeling heat transfer and mass transfer. Transfer and mass transfer and is phase change. The next problem that I will be posing you is the question number 30. That is like while deriving young Dupre Young's equation for contact line contact angle, you have to consider vertical force balance if. So this is the situation. This is the substrate. This is the liquid, gas, solid. Here you had sigma ls. Here you had sigma sg. Here you had sigma lg. So based on that, you have solved this by horizontal balance. Sigma sg equals to sigma ls plus sigma lg cos theta. Okay, if option A, B, C, D, substrate is flexible. If substrate is flexible, substrate is is deformable and fluidic. Substrate is rigid. Substrate is rigid. All of above. So you just think about this. Here you had horizontal balance. So when you have to consider the vertical balance, when you have to consider the vertical balance, like this is the sigma lg cos theta, getting equated with the sigma lg, but here sigma lg sin theta will be going up, so it is rigid, so you haven't considered it because these flows will be very insignificant if the interface is not deformable, but it is deformable. When it is deformable, then this will be, there should be a balance coming up. Then what is the correct answer for the same? So these are some options. You think about that. Meanwhile, I will be waiting a bit so that you actually think about the problem, and will I will catch you soon. So So if you have gave enough thought about this, then I suppose this, if it is flexible and if it is deformable, that is correct. This is wrong because here there will be no change. So only A, B is correct answer. A and B are correct. Okay, so that is the one case. And when you actually think, there are few questions that could be also asked, like question number 12, it was question 13. Question number 14 is, what is correct about squeezing resin? Okay, option A is droplet growth rate is directly proportional to the Q of dispersed phase, flow rate of dispersed phase. Another one is droplet growth rate is dispersed phase, and neck shrink shrink rate is directly proportional to Q continuous time needed to achieve needed to achieve squeezing squeezing is directly proportional to neck width divided by Q continuous divided by AB. And the last option is total length of the drop equals to drop growth rate into squeezing time. Which of the following is correct? If you actually remember the discussion that has been taught to you in the class, then you will come to know that this total length was the diameter of the T junction, the channel plus this. So this is the wrong, and these all are correct options. So A, B, C is the correct answer for the given problem about the squeezing squeezing board in the channel. And then and this in the dripping mode, there is the balance of viscous drag on the droplet and the surface internal interfacial force, which is the surface tension. So this uh, that is correct for the dripping problem. What are the three steps of bubble breakup? Question number 50. What are three steps of bubble breakup in flow focusing device. Flow focusing device. Okay, what are three steps of bubble breakup in flow focusing device? Three steps of bubble breakup in flow focusing device, and just think about this. It has been well explained, and I will be letting you know about. I will be telling you, but just think about that. The three steps are, what are the three steps of bubble breakup in a flow focusing device? So you know about the focusing device. So flow focusing device, flow focusing device is like this. Flow focusing devices are built in such a way that, for suppose this is the one stream of the continuous fluid coming up. This is the another stream. From here, one stream, one stream, one stream. Q disperse and Q quantity, and this is also Q quantity. And these are coming up like this. These are notches, and then this has to pass through some constriction over here, and then in something big one. So when this flow happens, here there will be neck formation, and there will be neck formation, and there will be dripping coming up. These flows are happening this way. So these are like flow focusing device. In this, gas enters the orifice and penetrates into the channel. So the steps are: gas enters the orifice and penetrates into the channel. A clearly visible neck develops. A clearly visible neck develops. Then the thread collapses rapidly and breaks because of Rayleigh plateau instability. The thread collapses, and breaks. Okay, so that is the one thing. So flow focusing device. So which of the following is correct for the volume of the flow bubble form? Question number 16 or 15. Let me see. 16. Which of the following is true for volume of the bubble formed? Option A is inversely proportional to E gas, inversely proportional to directly proportional to viscosity of the liquid, volume of V bubble, volume of bubble equals to pressure of the gas times divided by flow rate of the liquid times viscosity of the liquid, and the D option is non-undeniable. Which of the following is correct? And if you remember the exact discussion about the same in the second lecture of the week, you will come to know that option C is correct answer. So option C is correct answer for the same. And then the next lecture about the surface tension you came to know. Work up a dozen you came a discussion happened like between the same molecule there will be cohesive force, and between the different molecule there will be adhesive force. So based on that we will be solving one question based on the rise of the capillary. So so let me write these that question to you, and meanwhile uh, what happened, let me see. So we are having 8 minutes and we will be around 15 minutes we are having. So we will be solving three questions, and if Siju is there still, yes. So the question is so let me just first explain you, then we will go for question, or let's write the questions and we will be solving them one by one. The question is, if the surface tension of the water at the air interface, if the surface tension of water at air interface is 0.073 millimeter, 0.73 Newton per meter, then find P inside raindrop raindrop of 1 millimeter diameter in Pascal. So that is the question number, what is 17, and that is on the bench. So you solve it. So when you actually go for solving this problem, so there are some of the formulas that you should know. So pressure inside droplet, if you are going for that pressure inside droplet, then pressure inside droplet or pressure drop inside droplet, so that is delta P equals to 4 times surface tension divided by D if the droplet diameter is D. This is D. And if it is inside bubble or soap bubble, inside bubble, so that is delta P equals to 8 sigma by D. So this is bubble, this is drop, this is bubble. Bubble is having air inside. Again, this is D. And if this these two things you have to remember, and another one is capillary rise and fall. Capillary capillary rise and fall I will be telling you in the next problem. So no issues for that. So let's yes. So this question is, if the surface tension of the water at the air interface is 0.073, then find the P inside the raindrop at 1 mm diameter in the Pascal. You have asked to calculate. So for the drop, you know that delta P equals to what? Delta P equals to 4 sigma by D. Delta P equals to 4 times surface tension divided by D. So when you solve it, this is 4 times 0.073 divided by diameter of the drop is 0.001. So delta P is what? 292 Newton per meter square. This is excess pressure. Okay, this is excess pressure. So if you want to write, this is what? This is drop. Here P inside and P outside is there. This is diameter D. So P inside minus P outside. So excess pressure will be inside. It is 292 Newton per meter square. So this is what? P in minus P out is what? 10 to the power 5 Pascal equals to 292 Newton per meter square. When you solve it, this is P inside equals to 10000 plus 292. This is P inside equals to 100292 Pascal. This is the correct answer for the given problem. Okay, so this is the one question. And the another question is question number 18 is question number 18 is if dia of diameter of capillary tube is 1 mm, then capillary rise is 3 centimeter. What will be capillary rise when dia is changed to 0.2 mm? So what will be the capillary rise? So for the the thing that I wanted to tell you is capillary rise and fall. About capillary rise and fall. Okay, let me just clean it a bit down. Yes. So capillary rise and fall, that is denoted by H, and H is 4 surface tension times cos theta divided by density of the fluid which is inside times gravity times diameter of the capillary. So if 0 is less than theta is less than pi by 2, this is capillary, there will be capillary rise. And if why this is happening, you see the graph for the cos theta is this one. So 0 pi by 2. So if you are here, then in this one the value is of the cos theta is less than 1 and greater than 0, so you will be having some height which is non-zero. But in this case, if theta is greater than pi by 2, this cos theta becomes negative. So pi equals to cos x negative, and then there will be depression or capillary fall. So using this equation, so from here you know that H equals to 4 surface tension cos theta divided by density of fluid times gravity times diameter of the capillary. So this explains that H is inversely proportional to the diameter of the capillary. Means H1 by H2 H2 equals to D2 by D1. Okay, therefore H2 equals to D1 by D2 multiplied by H1 equals to D1 by D2. How D1 by D2? Means D H1 is D1 by D2 is what? You have you had 1 mm and now you are having 0.2 mm. So 1 divided by 0.2 multiplied by the initial was 3 centimeter. Okay, these are mm cancelled. So what you will get is 5. This is 15 centimeter is the height in the second one. So means what is the scene that got developed here is this one. Suppose this is the capillary, this was the bath, and you dip the capillary. The rise happened. When the diameter was 1 mm, the this height was suppose 3 mm. Okay, but when you had this thinned down, thinned down, this is 0.2 mm, then the height became here, which is 15 mm. 15 mm. So 15 centimeter, and this was 3 centimeter. So that is the correct answer for this. So the last question that I want to solve is the question related again to the soap film, like one drop we have solved. Just solve for one soap. So this question will be 19. Question number 19. This is consider a soap film bubble of diameter d. Consider a soap film bubble of diameter d if the external pressure P0 and surface tension of the soap bubble film slash bubble is sigma, the expression for the pressure inside the bubble. The expression for the pressure inside the bubble is, so this we have already discussed. So if you want me to discuss it again, like the formula we have discussed, and the formula was this one, uh, this one. So in that you have been provided with the options. So option A is P0, option B is P0 plus 2 sigma by D, option C is P0 plus 4 sigma by D, option D is P0 plus 8 sigma by D. So from here we see 8 sigma by D, this is P inside minus P out equals to P inside minus P out. This is expression inside bubble. From here you will have P inside to be P0 plus 8 sigma by D. So option D is correct. Option D is correct. So this is the one. But how it comes up? Option D is correct one. But how? Solving now. So let's solve it. So suppose this is your bubble. Okay. This is your bubble, and obviously if this is bubble, when you cut it, so there will be some outer thickness and there will be some inner diameter, some outer diameter if the bubble is of slight thickness. So if you consider this to be like this, and this red portion that you are here is the outer thickness, and this is the inner thickness, then there will be some forces acting. So the force is like, obviously this is the surface. Okay, so this side you will be having surface tension coming up from outer radius and inner radius, both it will be happening. This is P inside. P inside will be acting here to control this interface, and this is P outside. So the surface tension force which is there will be surface tension time perimeter, and this will be surface tension time pi d into 2 pi r is the perimeter. So two perimeters will be there. Negligible thickness. Assume negligible thickness of bubble. Okay, so that is there. So this is the one, and then force equals to let us take red color. Force equals to delta P times pi d square by 4. So whatever pressure difference will be there from inside and outside, that multiplied by area where this force is acting, that is the force, that is P in minus P0 pi d square by 4. So from here, equation 2, equation 1 was the above one. So equating equation 1 and 2, we get Pi minus P0 pi d square by 4 equals to sigma pi d into 2. So you will get Pi minus P0 equals to 8 sigma by d, means Pi equals to P0 plus Read Sima by read the correct answer. So that clears up this particular lecture and our discussion. I hope I have explained things which was relevant to the lecture of the week. And thank you so much, Sizu. And in the next lectures, next week, there will be some more discussions and some more questions which are yet to come. So thank you so much. So Siju, are you there? Yes, it's okay. So okay, thank you. I am exiting the call.